Welcome to the BC Calculus video for skill number 246, the Fundamental Theorem of Calculus. I can use the Fundamental Theorem of Calculus. Alright, if we want to create the Fundamental Theorem of Calculus, what we want to do is let's define a function, and we'll call that function, we'll call it g of x, and this function is going to be area under a curve. So it's the area under the curve from some point A to some point x, and that x value is our variable. So we want to take the area under the curve of some other function, so maybe we'll call that function f, and the curve is drawn with respect to t. So what we have here is a function which represents the area under the curve f. And on the next page I've got a diagram of this, so let's take a look at that. So we're defining the curve as f, and what we have here is some area underneath it, and we're going to let the curve be continuous on the interval from a to b. And in order to define the area, we're interested in the area from A to x. So I've created this kind of arbitrary point between A and B, which I'll call x. On this page I called it capital F of x. I also sometimes will use g of x, but we should kind of know that what's happening is either one of those variables work. The capital or the big F applies to our concepts of antiderivative. Anyways, we stated that this is equal to the integral from a to x of the curve f of t. So what this is doing is it's finding this shaded area right here. Alright, so now that we've taken or created this function, this big F, or if we want to call it g, let's ask ourselves what happens. Let's group these. Hold on. Alright, so let's ask ourselves what happens when we take the derivative of this. We're taking the derivative of big F of x, or if you wanted to write it, g prime of x. What we're doing is we're going to take the derivative of the left and right sides. So we take the derivative of the integral from a to x of f of t dt. And we want to evaluate what is the derivative of this integral. What the fundamental theorem of calculus tells us, and if you're interested in seeing a proof of this, there is a video on Khan Academy, but what the fundamental theorem of calculus tells us is that this is equal to the function of x. In other words, big F prime of x is equal to little f of x. That's what the fundamental theorem of calculus tells us. It tells us when we take the derivative of this integral, we get this relationship. If big F of x is equal to the integral from a to x of ft dt, then big F prime of x is equal to f of little x. So what? Why is this so fascinating and so big, so wonderful that it gets named the fundamental theorem of calculus? Well, first off, one reason it's pretty fascinating is it tells us that every single continuous function has an antiderivative. So when we learned about differential calculus, we were able to take the derivative of any function that we are given. However, when we get into doing integrals, we'll find that not every function is integratable, or not every function are you able to take the integral of. However, the fundamental theorem of calculus proves to us that every continuous function does have an antiderivative. We just may not be able to find it. The other fascinating thing that this does is it connects differential calculus to integral calculus. So this is pretty important that we can see or bridge these two pieces. Extending the fundamental theorem of calculus, or at least the first part of it, or what some people call the first part of the fundamental theorem of calculus, we can produce the corollary, or part 2 of the fundamental theorem of calculus. So the second part of the fundamental theorem of calculus allows us to state that the integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a, thus giving us a way to evaluate a definite integral if we're able to find the antiderivative. In the next skill, we'll focus more on the second part of the fundamental theorem of calculus, but let's focus a little bit on part 1 and see what we can do with that. Say we are given this function and we are asked to find the derivative of this function. What we notice here is we basically have the right half of the fundamental theorem of calculus. If I set this equal to big F of x, when we take the derivative of it, we're asking what is big F prime, and the fundamental theorem of calculus allows us to just write f of t. So the answer to this is equals, take f of t and replace the t with an x. So equals tangent of x over x squared minus root x. So the derivative of this integral is tan x over x squared minus root x. Looking at another example, example 1, we have this scenario, and we notice that we actually have x cubed at the top. And so what we have here is a case where this is equal to big F prime of x cubed. And so we have the chain rule, so we know what we can do is stick x cubed in for t. Or let's write this out real quick. Okay, so what we're going to do is we're going to use the chain rule. When we're asking ourselves, take the derivative of this integral, we're saying take the derivative of big F. And so what we can do is plug x cubed in for t, because that's our variable, but then we apply the chain rule. So remember, the derivative with respect to x is going to be the derivative of the outside times the derivative of the inside, or in other words, the derivative times 3x squared. So the derivative of the outside will give us cosine root x to the third over the natural log of x to the third, and then that all gets multiplied by 3x squared. And that is our answer. Right, in example 2, we have a case where our variable is actually in the bottom, and we can use the second part of the fundamental theorem of calculus so that we're able to rewrite this as negative, take the derivative of integral 8 to 2x to the fourth. So we're able to switch the boundaries, and you can use the second part of the fundamental theorem of calculus to see that. I demonstrated it in class as well. So what we have there, and then we just take our 2x to the fourth and plug it in for the t's, keeping in mind that we need to also apply the chain rule. So if this is all equal to the derivative of big F of x, except Rx is 2x to the fourth. So we need to apply the chain rule. That gives us a final answer of log root 2x to the fourth over sine of 2x to the fourth times the derivative of 2x to the fourth, which is 8x to the third. So knowing the fundamental theorem of calculus is nice because this would have been very, very difficult to evaluate without the fundamental theorem of calculus. We'd be perhaps searching for what is the antiderivative to this function for a very long time because it doesn't appear to have any clear antiderivative. Let's take a look at an example where both of the boundaries are in terms of x. So what we see here is a x in the lower boundary and x squared in the upper boundary. And so if you wanted to think about it, what we're looking for is big F goes from x to x squared, and we're trying to find the area under there. So one possible way that we could attack this is actually imagine a boundary between the two, which we'll just call call A, and we'll find the area from x to A and add that to the area from A to x squared. So we can rewrite this integral as being big F of x is equal to the area x to A of tangent t dt plus the integral of a to x squared tangent t dt. And since the problem's asking us to find the derivative, we want to take the derivative of each piece. So we get f prime of x is equal to the derivative of this integral, x to a tan t dt, plus the derivative of a to x squared of tan t dt. And when we go about evaluating this derivative, let's make some room here. This first one, we notice that the x is in the denominator, or not the denominator, in the lower limit with the a in the upper limit. So by making it negative, we can switch where the limits on that integral are, a to x, tan t dt. The second one, we can actually apply the fundamental theorem of calculus with the chain rule, and we get tangent of x squared times 2x, and then we finally apply the fundamental theorem of calculus to the first integral, and all of this is equal to negative tangent x plus 2x tangent x squared. Alright, so there's lots of ways that this can get presented. Typically, what I'd expect on the AP test is something like this, where you have to find the answer using the fundamental theorem, but it would be a multiple choice question. And if you understand the fundamental theorem of calculus, the way to the answer is much faster than perhaps evaluating what is the antiderivative of tangent of t and using the second part of the fundamental theorem. So what's the critical takeaway from this lesson? Whenever you see g of x is equal to the integral from a to x of ft dt, you can conclude that g prime of x is equal to f of x. More importantly, with a little work, we can use part 1 of the fundamental theorem of calculus to conclude part 2, which allows us to evaluate a definite integral.
You're beautiful.